let's, I guess, go ahead and get started. Welcome back. We're now done with the first third of the course, really. You should be getting back your homework 3 stuff tomorrow. And we're trying to get the midterms graded by the end of the week. So you should have those back in your hands. Hopefully on Friday, but certainly no later than next Wednesday. If we get them back on Friday, that still leaves 2 weeks to decide whether or not it's appropriate for you to drop the course for whatever reason. That's one of the reasons why we put the midterm where it is. I'll just say this now, if you have concerns at all about how you did on the midterm, the earlier you come talk to us, the better, either me or to one of the TAs. My general impression is that the midterm went fairly well. In particular, it went better than last semester. Good. Last semester's midterm was 8 questions in the same 2 hours. It was a bit of a bloodbath. I think this time went a little bit better. But until the actual numbers come out, that's you know, I can't say anything about what I expect the mean is going to be. Because I know from experience my estimates of these things are really bad until I actually do have the Excel spreadsheet in front of me. But if you do have questions or concerns about the exam, please do come talk to me in office hours, or come talk to one of the TAs in their office hours, or come talk to me after class. I don't think there should be any other administrative things to talk about, but if there are, happy to answer. Okay. So, we've been talking about, you know, except for the break in the middle of last week when we had this midterm, we've been talking about recursion. And the particular style of recursive algorithm that we've mostly been thinking about is divide and conquer, where the idea is I want to take a large problem and divide it up into smaller pieces, each of which has, you know, some fraction of the data from the original problem. Maybe it's half. I mean, something like merge sort's fairly intuitive. You split the array into 2 halves, do something, and then combine them back together. Maybe it's some somewhat more complicated recursive structure like the linear time selection algorithm, where you end up with subproblems that don't really correspond to distinct pieces of the data, but nevertheless, you have this kind of constant factor decay whenever you recurse. You're recursing on subproblems that are some fraction smaller than the original. And so you end up getting, you know, you split into subproblems of size, you know, n over c for some constant c. Not necessarily all subproblems with the same value of c. And then you analyze these things with recursion trees. Now, homework 4 is all about divide and conquer. The labs that you saw on this both last Friday and the Friday before, the algorithms that you looked at were all variants of binary search, which is sort of the canonical elementary divide and conquer algorithm. Do a constant amount of work, throw away half of the data, and recurse. But this is pretty much all that I want to say about divide and conquer stuff, up until you have the midterms to play with. The thing that I want to talk about next is a different style of recursive algorithm called backtracking. And the difference between divide and conquer and backtracking is mostly, from the sake of intuition, the big difference is you reduce to subproblems of smaller size, but instead of dividing by some constant, you remove some constant. Okay? So I want to think of it as, instead of, say, splitting into two problems, each of size n over 2, maybe I'm going to split it in, reduce it to two subproblems, each of size n minus 1. Okay? You can kind of think of the Tower of Hanoi as an intuitive example of this. Unfortunately, these algorithms, if you just implement them naively, end up always, like the Towers of Hanoi, taking you exponential time. But for now, I don't want to care about that. For now, I want to think of backtracking as a way of developing a correct recursive algorithm. And then later, we'll describe how sometimes, not all the time, you can take a backtracking algorithm and by doing a little bit of extra work, turn it into something that's actually efficient. Yes?
Are these two different approaches for different problems?
These are very fuzzy categories. Okay, there are problems like binary search where divide and conquer is sort of a natural way of thinking about it. But you can also think of the searching problem, find something in this array, as a backtracking algorithm where I look at the first element and decide whether it's the thing I'm looking for, and if it's not, I recurse on a problem of size n minus 1. It's a really trivial version of backtracking, and in that case, it doesn't give you something exponential. It just gives you linear. There are more complicated algorithms that actually combine both of these ideas, which we might actually see an example of at some point. But I think the distinction will maybe become a little bit clearer once I show you some examples. Right, so I'm going to veer off from my standard way of attacking algorithms problems, which is, here's the problem, let's develop an algorithm, let's argue that the algorithm is correct, let's figure out what its running time is. I'm going to leave out the last step, because in the end, I'm going to get something horrible and exponential, and, well, I'm just going to look ahead and say, well, most of the time I'll be able to improve that, or a lot of the time I'll be able to improve that. So let's not worry about this for now. Okay? I'm really just going to be thinking about trying to develop some sort of recursive strategy for solving a particular problem. Okay? So the problem that I want to start with is something that dates back. It's a puzzle that dates back to the mid-19th century. Called the 8 Queens puzzle. And this is, probably again, one of the canonical examples of a problem that's normally attacked by a backtracking algorithm. So, for any of you who don't know any of the rules of chess, the way that the puzzle is phrased is you're given an 8x8 board, an 8x8 grid of squares, and you want to place queens on some subset of them, in fact, on 8 of them, with the property that no pair of these queens is attacking each other. So you can't have 2 queens on the same column, you can't have 2 queens in the same row, and you can't have 2 queens in the same diagonal, either with slope 1 or with slope -1. Okay, because in the normal rules of chess, given, you know, if this were a white queen and that were a black queen and it's white's turn, white could move here and capture. Okay. All right, so this is one of several hundred essentially distinct solutions for this problem. And the puzzle was, well, you weren't actually given the solution, of course. You were given the chessboard, and you know, in the London Evening Standard, there was a picture of an 8x8 grid, and it says, "Put the queens down." How can you do it? Of course, we know how long it takes to solve this problem. How long does it take to solve the 8 queens problem? If you wanted to solve it from scratch, I mean, you know that you can do it because I showed you a solution, but how long would that take you? What's n? What is n? Number of what? Number of queens is 8, not n. So how long does it take to solve the 8 queens puzzle? How long does it take to solve the 48 million queens puzzle? Constant. It takes constant time to solve the 8 queens puzzle because there is a constant number of stuff that you have to do, and it's solvable. Okay, so of course you have the computer scientist instinct. That's good. The computer scientist instinct is that's a hard-coded constant. No, it isn't. Okay, the smart-ass computer scientist instinct is that's a constant. Okay. But let's make, you know, it's boring to say that, so let's make it interesting and we're going to solve the n queens problem. Okay, so how would we solve the n queens problem? So I'll just give you an intuitive idea of how a backtracking strategy might work. I can reason a little bit, so I'm not going to be completely blind about this. I can have at most 1 queen on each row. Did you have a question? No, I can't put more than 8 queens on an 8x8 board because then I'd have 2 on the same row. All right. So really, I should imagine this is an n by n grid, and I have n queens that I want to put down. And for technical reasons, those technical reasons being the solution doesn't exist otherwise, I want to assume that n is at least 4. So I know there's going to be 1 queen on the first row, 1 queen on the second row, and so on. The only question is where on the first row is the first queen going to be? Where on the second row is the second queen going to be, and so on. So I have no idea a priori where the first queen is going to go on the first row. So I could try to be clever, but at this point, I'm going to prefer to be lazy instead, and I'm going to just try putting it in slot 1. Now, something is going to go on in the rest of the board. Maybe it will return a solution, and maybe it won't. Okay? Some other subroutine is going to figure out how to put the queens on the rest of the grid. And if it succeeds, it'll come back and say, I succeeded, at which point I will say, aha, I succeeded. And if it failed, I'll say, oh, I guess this wasn't the right place to put the queen. Maybe I'll try here in slot 2. And then I will do something to fill in the rest of the board. And either it succeeds, in which case I'm happy, or it fails, in which case I say, oh, well, I guess space 2 wasn't the right place to look at it either. Let's try 3. And then I'll recursively or do something for the rest of the board. So the way that I decide where to put the queen on the top row is I try all possible places where I could put the queen in the top row. And then for each of those places, I check whether it worked by solving something that looks kind of like a recursive subproblem. Okay? I'm not trying to be clever in any way and say, oh, well, clearly I should put it in the top left corner because that attacks the fewest squares, and so that's going to leave the most space open for the other queens to go. Clearly that's the right thing to do. The moment you find yourself using the words clearly, obviously, just, that means you're wrong. Okay? Whenever you see the word obvious, this is a trick for reading papers. If you ever read a research paper and the paper uses the word obviously, that is very, very clear evidence that the sentence following the word obviously is actually false. Or clearly, or just. Just is a really horrible one. Oh, you just put it in the corner and recur. No, that just is hiding something. And the reason why the person who's explaining it to you wants to hide it under the word just is because it must be simple, I don't want to explain it because actually, in fact, I don't understand what's going on. But it'll make me look smart if I just say just. Okay? So I'm not going to do any of that. The choice of how I figure out where on the first row to put the first queen is I try all possibilities. Complete, utter brute force. But then for each possibility, I have a subproblem that I need to solve to fill in the rest of the board. Now, what makes this algorithm be a recursive backtracking algorithm is somehow I need to phrase the problem in a way that what I really am doing when I want to fill in the rest of the board is recursion. And that's not actually true if the problem is, can I put n queens on an n by n board? Because once I fill in the first column, the question I'm asking is now not, can I put the other n minus 1 queens on this n minus 1 by n board without, wait. It's not exactly the same problem anymore because I have to also avoid this column that collides with queen 1 and this diagonal that collides with queen 1. Okay? So the actual subproblem that I'm going to imagine attacking here. Okay, so maybe in the middle, if I just jump into the middle of my my recursion tree, the current state of the board is, well, the outermost level, I've decided to put queen 1 in column 3, and in the second level, I've decided to put queen 2 in column 7, and in the third level, I've decided to put queen 3 in column 2, and in the fourth level, I've decided to put queen 4 in column 4. What do I do to fill in the rest of the table? So the recursive subproblem is, I've already decided to put queens down above some line. Is there a way to put the rest of the queens down below that line? Okay. And so one of the arguments to my recursive subproblem is actually the positions of all the queens in the earlier rows. All right, now at this point, if I actually turn this into some sort of pseudocode, that checks for the rules and everything, I get a recursive algorithm that looks something like this. I don't want to step through the details with with one exception. Notice that the way that I decide, what this means is I've already got queens in the first r-1 rows. I want to put down the queens in rows r through n. And what I'm doing in this main for loop is saying, let's try all possibilities for putting down the queen in row r. And then for each one, I'm going to sort of recursively evaluate whether that works. Okay. Now, when you sort of try to think about how this algorithm behaves, you get something that, again, looks very much like the same recursion trees that we use for divide and conquer algorithms. And there's a reason for that. It's because it is the same kind of recursion tree. It's just that the sizes, if you will, of the subproblems aren't going down by constant factors anymore. In each subproblem, I'm considering I have one less free row than the subproblem that called it. Right? And so in this case, for 4 queens, I start at the top, and first I check queen 1 in column 1, and then it turns out I can prune away some subproblems by noticing that if I put queen 2 in column 1 or column 2, then I get a collision right away. Right? Queen 1 and queen 2 would attack each other. So there's only 2 places I could put the second queen. And if I put down queen 1 in column 1 and queen 2 in column 3, there's actually nowhere safe to put the queen on the 3rd row. So at this point, I don't have to recurse any further. Right? So I've done a little bit of cleverness to keep from having to recurse all the way down to the floor and then checking whether I have something legal. But still, I end up, with this tree-like structure that describes the pattern of recursive calls that the algorithm made that eventually lead down to the only 2 solutions for the 4 queens problem down at the leaves. Okay. Right. So this is a good example of the sort of general pattern of how backtracking algorithms work. You have some sequence of decisions that you need to make. And so you look at the first decision you need to make. You say, what are the possible things I could decide to do here? You don't try to cleverly figure out which one of those decisions is the right one. Rather, you just say, well, let's try them all. And then for each one, you try to recurse in a way that's consistent with the decisions you've already made. Okay? So this might be a little bit clearer if I give a more down-to-earth, possibly simpler example. So there's a problem called hey. Oh, okay. It's just out of focus. It's really out of focus. Really, really, really out of focus. Wait, oh, magic, okay. The trick is to get frustrated and then give up. Okay, all right, the SubsetSum problem. Okay, so the SubsetSum problem is the following. You're given a set X of, let's make it simple, positive integers. And you're given a positive integer T. And the question you want to ask is there a subset A of X such that the sum of the elements in A is exactly equal to T? Okay? So we could think of this as the following problem. I want to know if there's a subset of people in this room such that if those people took all the money out of their wallet and put it on the table, we would have exactly $374. No more, no less. Okay? So, what I'd like to be able to do is, faced with this problem, to make a simple decision that reduces the problem to a smaller instance of this subset sum problem. Exactly the same problem, but just involving something smaller. And in this particular case, the thing that I'm going to make smaller is the set. Okay? So I don't have any idea how big that integer t is, but I can sort of imagine, this is given to me as the input to a real algorithm. I'm given an array x, which has n integers in it, and I'm given one extra integer t. So when I recurse, I want to make the input size smaller, the number of numbers that I'm carrying around smaller. So I need to somehow make this set x smaller when I recurse. Right? So there's I want to make a simple decision, ask a simple yes-no question that would allow me to recursively, if I knew the answer magically, would allow me to sort of recursively pass the problem to the recursion fairy and be done. Can anyone, suggest, some simple yes-no question that might help make some progress? Yeah. Somebody pointed down here. So yeah. Don't worry about optimal.
So just check for every number, just check that and see if the remaining can give you 3 minus 7.
Okay, so the suggestion is, let's try to find one element that might go into A, if it exists. Right, what's the first element that I'm going to put into my subset? And now I've got a bunch of choices to make because I've got n possibilities for what that first element might be. And so I'm just going to try them all. Right? That will work, and it will give you an algorithm that with roughly the same running time as the one I'm thinking of. But that's a more complicated question than I wanted because you have n possibilities for what to ask. Which element do I try? I claim that there's an even simpler question where the answers are yes and no. Yeah?
Are any of them t?
Well, okay, so if one of the elements in the array is t, great, we're done. Even better, if t is equal to 0, great, we're done. Why? The empty set is a subset of X whose elements sum to 0. All right, so if I ever get t is equal to 0, great, I'm done. Is there any, well, I did declare t to be positive, so that couldn't actually happen. But I'll let you in on the secret, which is when we start recursing, that constraint is going to go away. So another way that we know we can always stop is if t ever goes negative, while x is a set of positive integers, and even the empty set of positive integers doesn't have a negative sum. Right? So then if the target sum t is negative, we just say no. Okay? Otherwise, okay, let's suppose t is positive, but it's not actually equal to any of the elements of the set. because you might be thinking this also, let's assume that none of the elements in the set are bigger than t. Because you can just throw those out. Yeah.
If you sum everything in X, it has to be bigger.
Okay, so you sum up everything in X, it has to be bigger in t. Okay, so this is all this sort of filtering that we can do that will speed things up, but if the filters all say, okay, sure, we passed that filter, we still have to actually solve the problem. So, okay, so suppose I'm faced with this particular set and a particular target value. Now, I know you could just look at this and go, yes, 3, 4, done. 1, 6, done. But you're clever and computers are not. All right? Yes?
Find the greatest element in X.
So the question is, can you find the biggest element? And I will adjust the input slightly to make this more interesting. I'll find the biggest element that is smaller than t, and now recurse on everything else and t minus that element. So now I would recurse on the set 5, 9, well, I could throw the 9 out, and t equals 1. And the answer would be, at this point I would say, well, no, because everything in the set is bigger than my target. What you just did is you tried to shortcut the brute force process. You tried to guess what you thought might be the right element to try. And it isn't always. Ah, okay, good. So there are two possibilities of what I might do with 6. I might keep it, and I might throw it away. 6 might be an A, and it might not be an A. Yes, it's an A. No, it's not. I like it. I hate it. Okay? Simple binary choice, and moreover, that choice is exhaustive. There are no other options other than, if this set A exists, either it contains 6 or it doesn't. And so the question that I'm going to ask is, well, does it contain 6 or not? Now, how do I figure out which of those two choices is the right one? I try them both. Right? Okay? I don't try to be clever and figure out which one. I just say, all right, fine. Let's try looking at it with 6 and try looking at it without 6. Okay, so I'm going to pick some element little x in X. Okay, if there is a subset A where the subset, these elements add up to t, then either little x is in A, or little x is not in A. Okay? If x is in A, what do I want the rest of the subset to look like? Can I say anything? Right, so now, at this point, what I want to do is I want to solve the SubsetSum problem for x without this element, little x. And now my target sum has changed. I've decided to accept little x into my heart, and that means that what I have left to put on the table is t minus x. Well, look, I have $7 in my wallet. Now I need a subset of everybody but me that has exactly 340 bucks. Okay? Now, the other possibility is that there might be a subset that doesn't involve the $7 in my wallet. And in that case, the way that I would figure this out is by throwing out x, the little x, the element I'm making a decision about, and recurse with the same target sum. I don't think my wallet is going to help, so I need to ask everyone else in the room if there's a subset of you with $374. Okay? And so if you put all of these things together, you get a recursive algorithm that looks like this. Okay? So the first line, if t equals 0, this is the base case where the empty set works, so I can immediately return true. The second, the else clause, if the target sum is negative, then I know there's no answer. I can return false immediately. And if there are no elements left in my set, but the target sum isn't 0, because I would have hit that in the if, then I also know the answer is no. There's no subset of the empty set whose elements add up to 5. So if I recurse my way down to the empty set in a target sum of 5, I know the answer is no. Otherwise, I make two recursive calls. Right? So the first recursive call is, let's suppose that the element, I picked the element at the end of the array, x sub n, to be the one that I asked the yes-no question about. So my first recursive call is, let's pretend that x sub n isn't necessary. The last element in my array is not going to be in the subset that I'm looking for. In that case, this recursive call to subset sum of the first n-1 elements in the same target should return true. The other possibility is that I really do want to keep the last element, what I was calling little x, and I'm now calling big X sub n. And so again, I recursively call this algorithm with this n-1 element array, but now I adjust the target sum downwards by the value that I've accepted. Okay? I make a decision. Well, I don't make a decision. I recognize that there is a decision to be made. There are two options. Either x sub n is in the set A that I'm looking for, or x sub n is not in the subset A that I'm looking for. I don't know which of these two options is the right one, so I try them both. If one of them succeeds, or if both of them succeed, I return true. There's a little logical or there in the middle. If they both fail, I return false. Yes? The V, that's a logical OR. That's a, it's C++ pipe. Bar, I don't know. What do people call that character these days? I grew up on Unix, so I think of this as a pipe character. So that's pipe. Probably you pronounce it OR, but that's the pronunciation for this little V symbol in the middle, so I don't use that. All right. You didn't see me draw that, did you? Okay, so recurse without the last element, recurse with the last element. But in each case, when I recurse, I'm recursing on an array of n-1 things. Anyone care to guess what the running time of this algorithm is? Not that it usually matters, but for backtracking stuff, but just to make sure we're all, somewhat awake. What's the running time of this algorithm? Well, maybe I should start by saying, can you think of a recurrence for the running time of this algorithm? So the running time is t of n, and, well, I do a constant amount of work doing the ifs and elses, and if all the ifs and elses pass, then I make two recursive calls, and for each recursive call, the size of my subproblem is n-1. Do you recognize that recurrence? Tower of Hanoi, perhaps? Except I put big O's around it, right? And how many moves did I need to make for the Tower of Hanoi problem? What do you think the answer is? Just guess. Good guess, provided you're using Emacs and you can type Control-T. You got the N and the 2 in the wrong place. It's 2 to the N. Every time you reduce the subproblem by 1, you double the number of subproblems. So if I reduce the subproblem from n down to 1, that means I'm doubling n times. That is the definition of 2 to the n. Okay? The other way that I could see why this might be 2 to the n is if you think about this for a while, you realize this is really just doing a brute force check of every subset of X. For every element, you say, is it there or is it not? 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 And there's some pruning, but eventually you're going to, for every element in your set, you're going to have a bit 1 or 0. And you're going to try all possible vectors of n bits, 1 for each subset of X. And so you're going to spend at least 2 to the n time. And the way that the recursion is set up, in fact, you're only spending a constant amount of time for every subset. So this is going to be, bad. Okay. Now, the bad thing about this example, the good thing is, it's a reasonably simple bit of pattern for recursion. The bad thing is that, in fact, you can't really do much better than 2 to the n. This is one of these problems, which we'll talk about in another month or so, that's NP hard. There is no algorithm for the SubsetSum problem that runs in time polynomial in n. Part of the reason for this is because t could be enormous, the target sum. But basically, the set of NP hard things, you can solve almost anything with the backtracking algorithm, but for an NP hard problem, that's more or less the best you could hope for. There's no way of saving running time using the techniques that we'll talk about later in the week and next week. Okay, so this is an example where really, it's not quite exactly the best you can do, but you're not going to be able to do better than exponential in something. All right. So for the next example I want to give, that's not true. In fact, there is a polynomial time algorithm for the problem I'm going to talk about next, and that polynomial time algorithm builds on intuition you get from thinking about it as backtracking. Okay. So are there any other questions about subset sum before I go on to the next example? It's a simple yes/no question. Is this element in the subset I'm looking for or not? I don't know. Try this, try that. Did either of them work? Okay. Okay, so we just had, a month of talking about regular expressions and finite automata, and you had an exam where you had to think about NFAs. So I know that NFAs are fresh in your mind, right? So if you remember what it means for a non-deterministic finite state automaton to accept a string, right? The question we're asking, so you're given some finite state machine, which consists of, and you're given a string. Okay. The question that I'd like to figure out is whether the machine accepts. And the formal definition is this massively ugly notation that basically says, is it possible to start in state S, follow a sequence of transitions labeled by the symbols in W, and end in an accepting state? All right? So formally, is there a walk or a sequence of transitions in M from S to an accepting state where the label of the, if I look at the labels on the edges and glue them together into a string, I get W. Okay. All right, so hopefully this definition is not a surprise or not, it's familiar. We know what it is. Okay, so it's always best to sort of think about a concrete example. So if we give a concrete example that I've used before. Zero, one. Okay, so this is an NFA that accepts any string that has either a 0, 0 in it or a 1, 1 in it. In fact, I don't really even need I don't need these middle transitions. Okay, so here's a nice little NFA. Okay, and my string is let's say 0, 1, 0, 1, 1, 0, 1. Okay. Now, when I start my NFA, I am in this state on the left. Now, when you think about one of the ways of thinking about how non-determinism works is when you read the first 0 in the input string W, you magically decide to stay put. Because I can look ahead and I'm clairvoyant. I can see the rest of the input. I can tell eventually I'm going to want to follow the 1, 1 path. So I know the right thing to do is to stay put. Computers are not so smart, right? What the computer's actually going to see is this. And now there's a 0 followed by some other stuff. I have to decide right now, do I stay put or do I branch to the bottom? Now, one of the other formalisms that you can think about with non-determinism is you just take both options simultaneously if you like, in parallel threads, or if you want to think of it as you maintain a set of states instead of a single state. I want to really nail this down to I have to decide on a single state. Okay. Based on the information that you have in front of you, here's the NFA, here's the state that I start in, the first symbol of W is a 0. How do I decide algorithmically whether to stay put or whether to go down? Try both. Maybe one of them will work. Don't try to think and outsmart the problem. Just look, if somehow I knew what the next state would be, then, if I knew somehow magically that this in fact is the next state, then the problem I have left to solve is, starting here, does the machine accept what's left? That's just a smaller instance of exactly the same problem. The recursion fairy will do it for me. On the other hand, if I knew somehow magically that the right thing to do was to go to the bottom state, again, I could just pass the problem off to the recursion fairy. Right? I don't know which of these two options is the right one, so I will try them both. Okay? Right, and so the algorithm is going to look something like this. Right now, the input to my algorithm is not only the machine is sort of written on the wall. Think of it as a global variable because I don't just want to keep writing it into the arguments when I'm not changing it. It's horrible programming style, but fine. Think of this as a method inside the machine object, so I don't have to keep talking about the machine. I need to pass in two things. I need to pass in what state am I currently in based on the decisions that I made in the past, and what string do I have left to read that will determine the decisions that I make in the future. Okay? And so I'm going to have a nice little Boolean variable here. Actually, no, I don't need that. So sorry. Let me start this over because I need to stop trying to be clever and just do things by brute force. Okay, so there are two possibilities for what this algorithm can do, and they depend on the definition of a string. Right, so there are two possibilities. Either W is empty or it isn't. If the string W is empty, then I return true if the state is in the set of accepting states for my NFA. That bracket, that means if the expression inside the bracket is true, 1. If the bracket inside the expression is false, 0. If you like, you can just say, this sentence has a Boolean value, and that's the Boolean value that I'm going to return. Okay. If the string is not empty, then I'm going to try all states that the transition function gives me. I'm going to write W as AX. For all states that I can get to in one step, if the DFA accepts, starting at state R, the suffix X, I'll return true. And then if I get all the way through this for loop without accepting anything, I'll return false. Okay? So this is my backtracking algorithm. I don't know what to do in the first step. Right? I don't know whether in this case to stay put or go down. So I'm simply going to try all possibilities of where I could go next, one at a time, by brute force. And for each of those choices of where to go next, I will attempt to solve the problem recursively. If the recursive problem works out, then hooray, my choice was correct. And then I immediately say, yes, this DFA will, starting at Q, will accept the string W. If all of the choices return false, then there is no good choice, and so no, there is no way to accept this string, and I return false. Okay? So I have one decision to make. What is the next step in the NFA? I have lots of possibilities to try. I try each one and then recursively solve the problem from then on. Right? Backtracking. Now, just so, again, we're on the same page, what happens if, I've read the first character already, and I decided, in one of my recursive subproblems to try the state down at the bottom, and the string I have left to read starts with a 1, and notice there's no outgoing arrow labeled 1. What does the algorithm actually do at that point? It returns false. It says, for all states R in the empty set, do something. Okay, done. I return false. So at that point, I don't make any more recursive calls. I just bottom out. I just fail immediately. Okay. So I need to make one decision and then try all possible ways of answering that one question, and then recursively see if that decision might have been the right one. Right? So we'll come back to this. You notice if you take this as written as a recursive algorithm, its running time is horribly exponential. Because every time you read a new symbol, you might have to go to an arbitrary subset of the states. So every time you read one of the n symbols, your recursion tree branches possibly by a factor of q, the number of states in the machine. So a crude upper bound on the running time is q to the n. Which, no, right? Remember that these things are often applied to pieces of code. Pieces of code tend to run in the millions of symbols. Anything to the millions is practically infinity. Okay? There aren't that many electrons. There aren't that many, if you believe in quantum mechanics, there isn't that much time. In the sense that time doesn't make sense below about 10 to the minus 180 seconds. And after 10 to the 100 seconds, roughly, you know, the universe just sort of fades out of existence. And so there are only 10 to the 200 moments, and maybe, you know, there's another 10 to the 100 reasonable places you could think of as a location in space, again, because space has a finite resolution. And so you can really only ever do about 10 to the 400 things. The universe will only do about 10 to the 400 things. 2 to the 1 million is bigger than that. So bad. All right. All right, so one more, and then we'll be done for the day. Okay. The longest increasing subsequence problem. A subsequence is kind of like a substring, except that the pieces that you pull out for that subsequence don't all have to be glommed together. Okay? So, so if I take if you can figure out where I started making up those numbers, good for you. Here. So a subsequence is basically, you know, a sequence is, I've not just got a set of numbers, but I actually have them in order in like a sequence, a string. And now a subsequence is basically a subset of that ordered sequence. Right? And a subsequence is increasing if every element in that subsequence is bigger than the elements that come before it. Right? So here in this 20-something element sequence, I've picked out an increasing subsequence of length 6. Right? This is not the same as the longest increasing substring. So this is one of the things that people get confused about, so I'm going to say it over and over and over again. A subsequence can be scattered. A substring is all together in one clump. Okay? Sometimes, just to emphasize that, say a contiguous substring as opposed to, you know, a possibly scattered subsequence. Okay, so really what I'm doing is I'm trying to pick out a subset of the indices, if you want, that has this particular property and is as big as possible. And the property is that if I look at the values at those positions in my array, they go up as the index goes up. Okay? So I'd like to make a decision, a choice, figure something out that would allow me to let the recursion fairy do most of the work. Yeah?
You can just start with 3 and say, does increasing
Okay. Right, okay, so keep or ditch. All right? Do I keep the 3 or do I throw it away? Well, it's sort of easy to imagine what you would do if, let's say, I'm looking now for the longest increasing subsequence of some array. And I'll ignore the base case because the base case is if n is less than 10 to the 400, just use brute force. Right. So either we want to keep x1 or we don't, right? If we want to keep x1, and if we don't want to keep x1. If we don't want to keep x1, then the thing we're looking for is the longest increasing subsequence of everything that's left. Okay? Starting at the second element and going up to n. And if we decide we do want to keep it, we need to say, well, yes, I accept this into my subsequence, and so my subsequence that I'm growing, if you like, now has length 1, and I have to figure out what comes after it. And so I would then recursively find the longest increasing subsequence of what's left. Something's not right. Because this says I should always keep. I want the larger of these two numbers. Because I'm trying to accept as many things as possible. If this were really the right logic, then I can just look at it and say, well, 1 plus blah is always bigger than blah. So I should always keep, which means I'm just going to loop through the array saying yes, 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 yes. And then I'm going to get the whole sequence as length n. I'm happy, I'm done. What went wrong? What went wrong, the right way to think about what went wrong is there is a word in the definition of the problem that I did not touch. All right? I haven't used every word in the statement of the problem. Something is wrong. I've ignored a constraint that the problem, I don't just want the longest subsequence. The longest subsequence is, in fact, the whole sequence. That is perfectly correct. But that's not the question I asked. Right? So this is not actually the right thing to do. And the reason it's not the right thing to do is the problem that I want to solve, once I've decided that, yes, I want to use the 3, isn't exactly the longest increasing subsequence problem. It's something a little bit different. Once I've decided, okay, I'm going to take the 3. What subproblem am I left with? Yeah. Right? Just say it one more time.
Like if you would pass in what.
Okay, so it's the right answer, but I want to take it apart into 2 pieces. And the reason I want to take it apart into two pieces is that you're mixing the problem that you want to solve and the algorithm that you're using to solve it. Okay? The problem that you want to solve is not longest increasing subsequence, but rather what is the longest increasing subsequence of some sequence X, where every element is larger than some number p. All right? So I'm not asking, the sub-problem is what's the longest increasing subsequence of the last n minus 1 numbers, where everything is in that subsequence is bigger than 3. And that clause, where everything is bigger than 3, means this is not the same problem as what's the longest increasing subsequence. I've added a restriction, right? This is actually exactly the same idea as we saw when we were looking at NFA acceptance. The recursive subproblem is not, does the NFA accept this string? The recursive subproblem is, does the NFA accept this string if I start at this state instead of S? Okay? So I need to take into account not only the part of the data that I haven't made any decisions about, but I have to also take into account the part of the data that I have already made decisions about. Stuff that I've done in the past versus stuff I've done in the future. Okay? So with that in mind, I have a recursive algorithm that might look like this. I pass in this second parameter p because it's part of the problem definition. Just as you said we should do. We should pass that number in. Okay? Now, again, ignoring the case when n is 0 or n is small because that's boring, there are a couple of possibilities. Either I want to use x1 or I don't, but it's possible that I can't use x1. Why? For example, here is now my new array x. This is my value p. Why can't I use x1? It's too small, right? So if x1 is less than or equal to p, then I know what to do. I throw one away, and I recurse on what's left. Right? I prune the recursion at this point because I know that if I took the 3 and then I took the 1, I'd get something that wasn't increasing. It wouldn't work out. So I'm going to prune the recursion tree now. Otherwise, well, I don't know whether to take the 1 or not. Well, let's say in this case, I've decided to throw out the 1, and now I recurse again. P is equal to 3, and x is now the array starting at 4. And I don't know whether to take the 4 or not. Okay? So in this case, I'm going to return the max of two possibilities. Right? The two possibilities are either I don't take x1, or I do take x1. What goes here? x1. Okay. Now, notice what I'm actually computing here is not the subsequence itself. I'm only computing the length of the subsequence. If you like, you could say here x1 dot and assume that you have some sort of data structure for subsequences that allows you to do concatenation like we did with strings. It turns out that when you want to find a structure like a subsequence or a path or a subtree or a subset, it's often sufficient to design the algorithm just to find the size, the length, the weight, the cost, some numerical function. And then once you've figured out how to do that, you can easily massage it to actually produce the real object that you're looking for. Once you have this recursive algorithm to find the length of the longest increasing subsequence, massaging it to return the actual longest increasing subsequence is not too difficult. Okay? This will be especially clear when we start doing this stuff efficiently. Right? But for now, keep in mind, I'm just looking for the length of the longest increasing subsequence, not the subsequence itself. Okay, so this is the subproblem that I wanted to solve from the very beginning. Once I've decided on whether to take the initial problem, what's the longest increasing subsequence, I decide yes or no, do I take the first one, and then I call this subroutine. Yeah?
If the array allows for negative numbers, so we would have to initially get 3 to the smallest negative integer, but we don't do that.
So the way that, this is an excellent idea, right? If I want to find the longest increasing subsequence of an array and I don't have a sentinel value, I don't have a previous value that I need to be bigger than, what do? I do that. The longest increasing subsequence is the longest increasing subsequence where everything is bigger than minus infinity. Right, so I don't need to have a separate routine where the logic is slightly different. I call LIS with one argument or LIS with two, depending on which case I'm in. Instead, I just reduce the problem to the problem with more arguments. And again, this is exactly the same thing that we would do here. I wouldn't have a separate subroutine that is, does the machine accept W? I would call this subroutine where the first argument is S. So this is a pattern actually now that we've seen several times. We saw something similar when we were doing median selection. It's often actually easier because it sort of naturally shows up in the recursive pattern not to focus on the problem that you're given, but realize once you do one level of recursion, you've slightly changed the problem. You made it a little bit more general, and then actually design an algorithm for the more general problem. And then in the end, you probably just need to set one parameter in the more general one to get your original more restrictive problem back. Okay. Anyone care to guess the running time of this algorithm? Guess. 2 to the n. You really like n squared. It's 2 to the n. And in fact, the way that you can see that it's going to be 2 to the n is imagine, if you will, that the array x is already in increasing order. Then what this algorithm is actually going to do is try every possible subsequence and eventually decide that the whole sequence is the right answer. But it's going to try all possible subsequences, and a subsequence is just a subset, and we know that they're 2 to the n subsets. Okay? It's just, in fact, except for that if statement, this is exactly the same pattern of recursion as we use for subset sum. So the running time is going to be the same. Okay? In the worst case. All right, so on Thursday, I will show you how to make this actually run in n squared time instead of 2 to the n. Thanks.